52,000 board feet. That is the daily output of a fully operational steam-powered sawmill in the Pacific Northwest. 1903, 52,000 board feet means enough lumber to frame approximately 35 houses in a single day, from a single mill, running a single head rig. Now understand what that required. No diesel engines, no hydraulic arms, no electric servo motors, no computerized feed systems, no OSHA, no machine guards, no emergency shutoff cables running to a safety panel on the wall. What powered 52,000 board feet per day was steam. Boilers, belts, iron gears, drive shafts spinning at 400 revolutions per minute, and men standing close enough to those systems that a single belt failure could strip a hand from a wrist in approximately 1/5 of a second. This is not a story about the men. This is a story about the machines, what they were built to do, how they actually worked, why they were extraordinarily dangerous by design, and what happened when physics and economics met in a building made of wood, surrounded by sawdust, next to a boiler burning at over 400 degrees Fahrenheit. The timber industry between 1880 and 1930 was one of the largest industrial operations in American history. It was not romantic, it was not poetic. It was a supply chain problem solved by mechanical force. Forests became lumber. Lumber became railroads. Railroads became cities. The machines that made this happen were loud, hot, relentless, and extraordinarily unforgiving. Let's go through them, one by one. To understand why these machines were built the way they were, you have to first understand the scale of the problem they were built to solve. By 1880, the forests of New England and the Great Lakes region were largely exhausted. Decades of logging had taken the white pine, the hemlock, the cedar. What remained wasn't economically viable without dramatically more expensive hauling operations. The industry moved west, into Michigan, into Minnesota, into the Pacific Northwest, into the coastal redwood forests of Northern California, into the Douglas fir stands of Oregon and Washington. These were not the forests of the Northeast. A Douglas fir in the Cascades could stand 250 feet tall and measure 8 feet in diameter at the base. The base. Before the first taper, a single tree of that size contained enough usable timber to frame an entire house, and it weighed, when felled, somewhere between 50,000 and 100,000 pounds, depending on moisture content and species. You could not move that with horses, not efficiently, not in volume, not through the terrain where these trees grew. Steep hillsides, river valleys choked with undergrowth, coastal ranges with grades that would break a horse's legs going downhill. The demand side of this equation was equally enormous. Between 1880 and 1920, the United States was building railroads at a rate that required hundreds of millions of board feet of tie lumber per year. Cities were expanding. Chicago, Seattle, Portland, San Francisco, all required structural lumber at a volume that pre-industrial harvesting could never supply. The industry needed machines that could fell trees, move logs, and convert raw timber into dimensional lumber faster than anything that had existed before. And they built those machines. They built them from iron and steel. They powered them with steam. And they deployed them in environments where, if something went wrong, there was often no way to stop it in time. The first machine we need to understand is not a saw. It is not a mill. It is the machine that made large-scale logging physically possible in steep terrain. It is called the steam donkey. The name is not industrial branding. It is a direct replacement for the animal. Before these machines, teams of oxen or horses dragged felled logs through the forest to the nearest water source. This method worked on flat ground. It became functionally impossible on a 40-degree slope in the Coast Range of Oregon. A steam donkey is, at its core, a stationary steam engine mounted on a heavy wooden sled. The sled is usually constructed from timbers 12 to 16 inches square. Old-growth fir, the machine itself weighs between 4,000 and 20,000 pounds, depending on the model and year of manufacture. Early versions from the 1880s were compact. By 1910, the larger Dalbier and Washington Iron Works models were the size of a small locomotive boiler section. Here is how it works. The boiler is fired with wood, often wood waste from the logging operation itself. Water in the boiler heats to the point where steam pressure builds. On a working donkey, operating pressure ran typically between 100 and 175 pounds per square inch. Some later models pushed 200 psi. That steam pressure drives a piston. The piston is connected by crankshaft to a large horizontal drum, the capstan or jippo drum, depending on the function. Wrapped around that drum is a cable, high carbon steel wire rope, 3 slack 4-inch to 1 and 1 and 4-inch in diameter in most applications. That cable ran out from the machine through the timber, sometimes a mile or more, to a choker, which is a short cable loop that a worker called a choker setter would wrap around the base of a felled log. When the engineer opened the throttle, steam pressure engaged the drum. The cable drew tight, and the log moved. In controlled conditions, this was a highly efficient system. In operational conditions, steep slopes, wet ground, broken terrain, old cable, an inexperienced engineer, it was not. The cable was the first point of failure. Wire rope under tension stores energy. When a cable under full load parts, snaps, it does not go slack. The stored elastic energy releases instantly. A 1-inch wire rope under 30,000 pounds of tension, when it breaks, recoils at speeds that contemporary accounts describe as invisible. You do not see it coming. You hear the report, a sound described by survivors as similar to a rifle shot. And then, whatever the cable contacted is already damaged. Choker setters worked in proximity to these cables. Their job required them to be near the logs while the cable was being attached, and then to clear the area before the engineer applied tension. The clearing signal, usually a horn or bell on the donkey, gave them time to move. If the signal failed, if a man slipped, if the log began moving faster than anticipated across angled ground, the math did not favor the worker. OSHA's predecessor agencies did not regulate the logging industry substantively until the 1960s. In 1905, the industry tracked production numbers carefully. Worker injury statistics were kept inconsistently, if at all. Let's go deeper into the boiler itself, because this is the system that everything else depends on, and it is the system that, when it failed catastrophically. The fire tube boiler used in most steam donkeys of the 1897-910 period consists of a cylindrical steel shell filled with water. Running through that water are a series of smaller tubes, the fire tubes, through which the hot combustion gases from the firebox pass on their way to the smokestack. The surface area of those fire tubes is where heat transfer happens. Water surrounding the tubes absorbs heat and converts to steam. That steam collects in the upper section of the boiler, the steam space where it builds pressure. The pressure is managed by a safety valve, a spring-loaded valve set to release at a specified pressure, say 150 psi. When pressure exceeds that threshold, the valve opens, releases steam, and pressure drops. Here is where engineering and operational reality diverged. Safety valves were mechanical devices. They wore. They corroded. The spring that controlled the relief pressure could be weakened by heat cycling or could be deliberately modified, weighted down, or wired shut by operators who wanted to run higher pressure than the valve was set for. Higher pressure meant more pulling power on the cable drum. In short-term production terms, it also meant a boiler operating above its design rating. The boiler shell itself was riveted construction, not welded. The iron or steel plates were formed and then fastened together with iron rivets driven hot and peened over. A rivet joint, properly executed, was strong. A rivet joint with a corroded plate, a bad rivet, inadequately lapped seam, or a hairline crack developing in the shell material, under pressure, was a contained explosion waiting for a trigger. When a boiler shell fails under pressure, the failure mode is not a leak. It is not a gradual rupture. If the failure is significant, a plate letting go, a seam opening, the pressure differential between the interior and the atmosphere is resolved in milliseconds. The water in the boiler, which has been maintained in liquid state only by that pressure, flash converts to steam. The volume expansion ratio of water to steam at atmospheric pressure is approximately 1700 to 1 pine. The boiler does not explode in the conventional sense of combustion. It is a pressure vessel failure. The mechanical result is similar. The shell becomes shrapnel. Steam and boiling water move outward at velocities that physical structures in the immediate area cannot withstand. Boiler explosions were not rare in the early logging industry. The U.S. Steamboat Inspection Service, later expanded to cover stationary boilers, documented hundreds of industrial boiler failures per year in the early 1900s. Not all were catastrophic. Some were slow leaks that scalded a fireman. Some were complete shell failures that destroyed an entire donkey and everything near it. The industry knew the risk. The solution was to train engineers to monitor pressure gauges and water levels, and to conduct visual inspections of the boiler before starting each shift. Visual inspection on a boiler whose failure mode was internal. You were looking at the outside of a vessel for evidence of what was happening on the inside. The steam donkey solved the problem of moving logs on a hillside. It did not solve the problem of moving them over distance to the mill. For that, the industry developed a different class of machine. In the northern tier states, Maine, Michigan, Minnesota, Wisconsin, winter logging operations used a different geography. Frozen ground, snow-packed roads, conditions where a wheeled vehicle would have been useless, and where a horse team could haul a sled over ice, but could not sustain the volume needed to feed a large mill. In 1901, Alvin Lombard of Waterville, Maine, received a patent for a steam-powered log hauler. The Lombard hauler is significant not just for what it did, but for how it was built. It used a continuous track system on the rear, crawler tracks driven by the steam engine. That could propel the machine and a train of loaded sleds across snow-packed roads under conditions no wheeled vehicle of the era could manage. The Lombard ran on steam, a vertical or horizontal boiler, wood or coal-fired, producing pressure in the range of 150 to 200 psi. That pressure drove a reciprocating steam engine, which turned the rear track drive through a reduction gear assembly. The front of the machine steered on skis. It was, mechanically, closer to a locomotive than to anything that came before it in land transport. The load it could pull was substantial. A single Lombard could haul a train of 6 to 12 loaded sleds, each carrying several thousand pounds of logs, across a prepared snow road. Horse teams could not match this volume. The machine could also operate in temperatures where horses became dangerous to work, below 0 Fahrenheit, in darkness, on roads through forests that offered no windbreak. The operational environment of the Lombard in northern Maine or Minnesota winters was brutal by any physical measure. Temperatures regularly fell to -20 or -30 Fahrenheit in active logging areas. The machine's steam plant required a fireman working constantly to maintain pressure. The engineer operated from an open or partially open cab. There was no enclosed heated space. Grease in the gear housings thickened in extreme cold and had to be managed constantly. Water in the boiler feed lines could freeze between the tank and the injector if the machine was not kept running. The Lombard's crawler tracks were an early implementation of a concept that would later define military and construction equipment. The principle, distributing the machine's weight over a continuous loop of track rather than concentrating it on wheels, allowed operation on surfaces that would trap a wheeled vehicle. Snow, soft ground, boggy terrain. This was not accidental engineering. It was a direct mechanical response to operational reality. Once logs reached the mill, by river drive, by rail, by skid road, by the cable of a steam donkey, they entered a second category of machine, the sawmill. A steam sawmill of the 1890s-1910 period was not a simple operation. It was a sequence of connected machines, all driven from a central steam plant, all linked by a belt drive system running from a single power shaft. If the boiler went down, every machine in the mill went down. If the main drive shaft failed, the same result. Let's walk through the sequence. Logs arrived at the mill pond or log deck. From there, a bull chain, a large continuous chain with dogs, which are steel spikes that bite into the wood, carried logs up an inclined ramp called the jack ladder into the mill. The jack ladder was one of the first danger points. Logs rolling on the chain, tipped or positioned incorrectly, could slide back. The chain mechanism itself could catch clothing, boots, hands. The log moved from the jack ladder onto the carriage. The carriage is a wheeled sled running on rails that held the log in position while advancing it through the head rig, the primary saw. In the 1890s, most large mills used a circular head saw, a disc of high-carbon steel, typically between 48 and 72 inches in diameter, spinning on a mandrel driven by the central line shaft through a belt. Rotation speed varied by mill and saw diameter, but 400 to 600 RPM was common. At 54 inches in diameter running 500 RPM, the teeth at the rim of that saw are moving at approximately 118 feet per second. 118 feet per second. A sawtooth moving at that speed, contacting an arm, does not cut in the way a kitchen knife cuts. The mechanics are different. The tooth is moving faster than pain receptors can process. By the time a worker registers that contact has occurred, the physical consequence has already happened. By the early 1900s, bandsaws were increasingly replacing circular head saws in large mills. The bandsaw, a continuous loop of flexible steel running over two large wheels, offered advantages in kerf width, the amount of wood wasted as sawdust per cut, and could handle larger log diameters more efficiently. The trade-off was tension management. A bandsaw blade running on wheels 6 to 8 feet in diameter at high speed carries significant lateral tension. Blade breakage. The blade snapping and the ends whipping free was a known failure mode. In a confined mill environment, a broken bandsaw could travel a considerable distance before losing momentum. The sawyer, the man operating the head rig, was a skilled position. He determined how to break down each log, maximizing board yield while managing the variations in log geometry, taper, sweep, internal defects. A good sawyer could read a log and make decisions in seconds that determined how much usable lumber came out of it. He was paid accordingly, more than most mill workers. He was also the person standing closest to the head rig. From the head rig, slabs and boards moved to the edger, which trimmed rough edges to consistent widths, then to the trimmer, which cut boards to length, then to the green chain, a continuous conveyor where workers called chain pullers grabbed boards by hand and sorted them by dimension. Every stage was mechanical. Every stage ran continuously. The central drive system, the line shaft, ran the length of the mill. It was a rotating steel shaft, typically 3 to 5 inches in diameter, suspended from the ceiling on pillow block bearings at intervals of 10 to 12 feet. Flat leather belts ran from pulleys on this shaft down to individual machines. A mill of any significant size had dozens of these belt runs. The flat belt was not a passive component. Under load, running at speed, a flat leather belt on a 12-inch pulley carries significant tension. A belt failure, a seam letting go, a belt jumping a pulley, produced a free end of belt moving at shaft speed. Early sawmill safety codes, where they existed, required belt guards. Implementation varied by ownership and attitude. The dust was also a variable that the machines created and that the environment made dangerous. A running sawmill produced sawdust continuously. It collected on floors, coated surfaces. It suspended in the air of the mill in concentrations that, under the right conditions, heat source, ignition point, sufficient suspended particle density, created a fuel-air mixture capable of deflagration. Sawmill fires were common. The combination of dry sawdust, hot bearings, and open firebox proximity produced fires regularly throughout the industry. Some were extinguished quickly. Some consumed entire operations. Step back from the machines for a moment and look at where they operated. A logging camp in the Oregon Coast Range in 1905 was not a fixed facility. It was a temporary settlement built in proximity to the timber, moved periodically as the accessible timber was cut. Buildings were rough-built. Some were constructed on skids so they could be moved by the steam donkey itself. The bunkhouses, long, low structures holding 20 to 40 men in bunks stacked 3 high, were heated by wood stoves. Ventilation was minimal. The steam donkey operation took place on hillsides where the gradient could exceed 60%. Ground conditions in western Oregon and Washington meant mud for 9 months of the year, the debris left after felling, the broken branches, the bark, the tops of the trees, covered the ground and created an irregular surface that could conceal holes, unstable footing, and the cables themselves. The noise level of an operational donkey in the timber was significant. The exhaust of a steam engine at work produces a rhythmic percussion that carries the cable. When under tension and moving through the blocks and fair leads, the guide pulleys used to redirect the cable's path produces a low vibration that you feel through the ground before you hear it. Clearly, communication between the engineer and the crew in the timber depended on signal systems, bells, whistles of specific number and duration to convey specific commands. Because voice communication was not reliable at distance in that noise environment, in the Pacific Northwest winter, you add rain, consistent rain. The roads through the timber, where they existed, were skid roads, logs laid crosswise in the path of log movement, greased with oil or animal fat to reduce friction. In heavy rain, a greased skid road on a hillside slope is not a stable working surface. The mill environment was different, but equally demanding. A large sawmill running full production was loud in a way that has a specific character. Not the impact noise of construction, but a continuous, layered mechanical sound. The rhythm of the carriage return on the head rig, the whine of the saw blade varying pitch as it entered and exited a log, the clatter of boards hitting the green chain, the hiss of steam from the boiler room, the slap of drive belts. Workers in these environments did not have hearing protection. Over a career of 10 to 15 years in a sawmill, significant hearing loss was a predictable outcome. It was not considered a workplace injury. It was considered a consequence of the work. The temperature inside a mill varied with season, but was uniformly high near the boiler room and the line shaft bearings, which generated friction heat continuously. In summer months in inland Oregon or California, the mill interior could reach temperatures significantly above ambient. Workers wore wool, practical in rain and in the timber, which became uncomfortable in the mill heat. There was no scheduled water break. There was a production schedule. Let's go through the specific failure modes in detail, not for dramatic effect, because understanding what went wrong is the only way to understand what the engineering limitations actually were. Cable failure. Steel wire rope and logging service experienced high cycle loading. Every time the drum turned, cable was paid out and taken up. The cable ran through blocks, pulleys, which bent it around a radius. Repeated bending at the same point caused fatigue in the individual wires. The wires, each of which is under tension when the cable is loaded, began to break individually. A wire rope showing broken surface wires was a signal that the rope was approaching failure. Whether that signal was acted upon depended on whether an experienced eye was examining the rope and whether the production pressure of the operation allowed for cable replacement before a failure occurred. When a wire rope fails under tension with a full log on the other end, the failure is sudden. The log, which has been under cable tension, may shift or roll when that tension is released. The cable end recoils. The area in a direct line from the failed section, the bight of a cable under tension, is the most dangerous zone. Documentation of cable-related injuries in the industry consistently identifies the choker setters and rigging crew as the most frequently injured category of worker. Log movement. A log on a steep hillside freed from a cable or rolling off a log truck follows gravity. It does not follow a predictable path. A 60-foot Douglas fir log weighing 30,000 pounds rolling down a 45-degree slope is not a thing that a person can stop, or redirect, or outrun in all-terrain conditions. Saw contact. Circular and bandsaw injuries in sawmill operations were recorded by the Bureau of Labor Statistics in several states from the early 1900s onward. The injuries were consistent with the machine's characteristics. Not the depth of cut that mattered, but the speed. The head rig saw a tooth did not catch clothing and pull a worker in. That was the belt system's failure mode. The saw, if contacted, resolved the contact immediately and completely. Recovery and return to work were not typically outcomes for saw contact injuries involving the blade in motion. The band saw breakage event was categorized separately. A snapped band saw blade in a large mill was a different type of incident. The blade, which was a continuous loop of several feet of steel spring under tension across two large wheels, when it fractured, released that stored energy. The ends of the blade moved through the mill space at speed before contacting a structure or losing energy. Guards existed in some mills. In others, they did not. Industry publications of the era documented specific band saw breakage incidents at mills and the resulting path of the blade through the building. Boiler failure, already discussed in terms of mechanics. Worth noting the operational context. A sawmill boiler served a dual purpose in winter. It heated the mill building through steam pipes in addition to providing power. The boiler ran continuously. The fireman's shift was the most physically demanding in terms of continuous manual labor, feeding wood into the firebox, managing water level through the injector, reading the pressure gauge. A tired fireman on a night shift could allow water level to drop below the crown sheet, the top of the firebox, which was water-cooled on the interior. If the crown sheet was exposed to firebox temperature without water cooling it, the metal lost structural integrity rapidly. When feed water was then reintroduced, the injector opened to restore water level. The cold water contacted the superheated crown sheet, and the resulting thermal shock could fracture the sheet. A fractured crown sheet under 150 psi was not a slow event. Belt system. A flat leather belt running at line shaft speed on a 6-inch pulley. If it jumped the pulley, became a free-moving length of leather moving at the speed of the shaft's surface. On a 4-inch diameter shaft turning at 200 RPM, the surface speed is approximately 200 feet per minute. The belt, freed from the pulley, could strike workers on either side. Belt guarding in early sawmills was inconsistent. The National Safety Council, founded in 1913, began publishing belt guarding standards, but adoption across the industry was gradual. Sawdust fires. The fire risk in a sawmill was not theoretical. In 1905, the Pacific Coast lumbermen documented 37 sawmill fires in the Pacific Northwest that caused total or partial destruction of the affected mill. Sawdust on hot bearings was a consistent cause. The solution: regular bearing inspection and lubrication, sawdust removal from bearing areas, required consistent maintenance practice. In mills running 2 10-hour shifts with a minimum crew, consistent maintenance practice was in tension with continuous production requirements. The workforce that operated these machines was stratified by skill and by risk. At the top of the skill hierarchy in a sawmill was the sawyer, the head rig operator. A capable sawyer earned $3.50 to $5 per day in Pacific Northwest mills circa 1905. This was significantly above the general laborer's rate of $1.50 to $2. The sawyer's decisions directly determined log recovery, the percentage of the log's volume that became saleable lumber, and therefore the mill's profitability. Good sawyers were recruited by competing mills. Below the sawyer were the edgermen, the trimmermen, the carriage setters who controlled the advance of the carriage between cuts. Each was skilled in a specific mechanical operation. Each worked in proximity to running machinery for 10 to 12 hours per shift. The green chain was the entry-level position in the mill. Chain pullers grabbed boards as they came off the conveyor boards that were sometimes still dripping with mill pond water, hence green, and stacked them by dimension. It was constant, physical, repetitive labor. The wages were the lowest in the mill. The turnover was the highest. In the logging camp itself, the hierarchy was different. The faller, the man who felled the trees, was the highest skilled position and typically worked in pairs for safety. Fallers read the tree for lean, defects, internal rot, and determined the fall direction to minimize damage to the log and maximize safety. They earned premium wages because their judgment was the first point of control in the entire process. Below them were the buckers, who cut felled trees into log lengths. Then the rigging crew, the hook tenders who supervised cable rigging, the chokermen who set the chokers, the signalmen who relayed commands between the crew and the donkey engineer. The immigrant workforce was substantial throughout the industry. Scandinavian workers, Norwegian, Swedish, Finnish, dominated the Pacific Northwest timber workforce from the 1880s through the early 1900s. They brought experience from Scandinavian forestry and adapted to the larger scale of American West Coast timber. Eastern European immigrants entered the workforce in numbers through the early 1900s as the industry expanded. Chinese labor, which had been heavily used in railroad construction and mining, also appeared in mill operations in California and the Pacific Northwest, particularly in the lower wage positions. Language barriers and mixed crew operations were a real operational factor. The signal systems, bells and whistles, were developed partly because they communicated across language barriers. A steam whistle blast pattern meant the same thing regardless of what language a worker spoke natively. The systems were imperfect. Misunderstood signals occurred. The work week was 6 days. The shift was 10 to 12 hours. There was no paid overtime concept in early 20th century logging. There was a wage and a shift length. If production demanded extended time, it was expected. The alternative was to leave, which meant leaving the camp, often in a remote location accessible only by company rail or road, and losing your accumulated bunk and board charges against your wages. The company town model was prevalent in larger operations. The employer owned the bunkhouses, the cookhouse, the company store. Wages were paid partly in company scrip credit at the company store. The net result was that a worker who needed to leave an operation might find that his accumulated charges against wages left him with little actual cash. This was not illegal in most states until well into the 20th century. This is the economic structure the machines operated within, not as moral commentary. As operational context, these machines were not maintained to a systematic standard in the modern sense. There was no documented preventive maintenance schedule. There was no condition monitoring. There was operational experience, the engineer who could tell by listening to the boiler that something was developing, and there was breakdown-driven repair. The steam donkey required consistent grease application to the crank and rod bearings. The oil cups on the steam cylinder required filling. The packing on the steam chest, the material that sealed the piston rod against steam leakage, wore and required replacement. A piston rod with inadequate packing leaked steam. Leaked steam on a cool morning in the timber became a visibility hazard, obscuring the engineer's view of the cable and the signal flags. Steam leaks also reduced efficiency. Pressure lost through leakage was pressure not available at the drum. The cable drum itself was a wear item. The cable, winding and unwinding under load, wore grooves into the drum surface over time. An unevenly worn drum caused uneven cable layering, cable spooling over itself incorrectly, which could result in crushing loads on the underlying layers or sudden jumps in cable level that affected tension control. The log carriage in a sawmill ran on steel rails. The carriage wheels, small flanged wheels supporting substantial load, required lubrication and periodic inspection for wear and flat spots. A carriage wheel with a flat spot created an impact load each revolution, a rhythmic shock transmitted into the carriage, the log, and the rail. Over time, impact loads on the rail joints worked the spikes loose and created rail irregularities. A carriage operating on irregular rails could rack twist laterally, causing the log to shift in the carriage dogs. The headrig mandrel bearings, the bearings supporting the saw blade shaft, were a critical maintenance point. These bearings operated at high RPM under the radial load imposed by blade tension and the cutting force of the saw. Inadequate lubrication caused heat buildup. Excessive bearing heat could cause the shaft to expand within the bearing, increasing clearance, and in extreme cases causing the mandrel to seize. A seized mandrel while the belt was still driving the pulley was a structural event. Saw blade maintenance, filing and setting the teeth to correct geometry, was performed by the saw filer, who was another skilled position. A badly filed saw wandered in the cut, produced a rough surface, and placed lateral loads on the blade that it was not designed to carry. Over time, these lateral loads could create fatigue cracks in the blade body. A blade that developed a crack propagating from a gullet, the notch between teeth, and was not caught in inspection, could fail during operation. The refractory lining of the firebox, the heat-resistant brick that protected the firebox shell from direct flame, required periodic inspection and replacement. Refractory bricks cracked under thermal cycling. A cracked refractory section allowed direct flame contact with the boiler shell material. The shell material was designed to be water-cooled on the interior. Without water coverage in that area, the metal heated, lost strength, and could develop a hotspot that eventually failed structurally. The Lombard log hauler's track system required consistent inspection of the track links, the pins connecting them, and the drive sprockets. A broken track link on a loaded machine on a snow road could cause the track to come off the drive sprocket, what the later military would call throwing a track. A machine of 15,000 pounds without one track on a sloped snow road was in an unstable condition. All of these failure modes were known to experienced operators. The question in each case was whether the operational pressure, the production schedule, the contract deadline, the foreman's instruction, allowed time for the maintenance that the known failure modes required. The machines justified their cost through output. The U.S. timber industry's production expanded dramatically between 1870 and 1910. National lumber production, all species, all regions, was approximately 13 billion board feet in 1870. By 1906, it had reached 46 billion board feet, more than triple the volume in 35 years. This expansion did not happen because 3 times as many workers entered the industry. It happened because the machines multiplied the output per worker. Graphic, U.S. Lumber production chart, 1870 to 1920. A steam donkey could move in one day what a team of oxen would require several days to move over the same terrain. A steam-powered circular mill with a skilled sawyer could cut 50,000 board feet in a shift. A 2-man whipsaw crew cutting by hand could produce perhaps 100 to 200 board feet in a day under good conditions. The scale difference is not incremental. It is several orders of magnitude. This production supported the railroad expansion of the late 19th and early 20th centuries. The transcontinental rail network required not only the ties, wooden cross members under the rails, but the trestle timbers for bridges, the station structures, the telegraph poles, and a fuel wood for wood-burning locomotives in the earlier period. All of that material came out of the timber industry, and the volume required would have been physically impossible to supply without the steam-powered machinery. City construction drew equally heavily on the lumber supply. The balloon frame house, the construction technique that allowed rapid residential expansion in American cities beginning in the mid-1800s, required consistent dimensional lumber and volume. 2x4s, 2x6s, 1x12 sheathing boards. These were not handcrafted items. They were standardized products produced by machine to consistent dimensions. The consistency itself, lumber you could count on being the same size, was a product of the sawmill's mechanical precision. A carriage setwork advanced to the same dimension each pass produced, boards of consistent thickness. Pre-industrial sawing by hand did not produce that consistency reliably. The economic geography of the Pacific Northwest was substantially shaped by the timber industry in this period. Portland, Oregon, grew as a timber shipping port. Seattle developed in direct relationship to the Puget Sound mills. Tacoma, called the City of Destiny in promotional literature of the period, was built partly on timber and partly on the railroad terminus. The mills were not incidental to these cities. They were foundational to them. The capital investment represented by a large steam sawmill was substantial for the period. A fully equipped Pacific Northwest mill in 1900 might represent $50,000 to $150,000 in capital. Boilers, machinery, buildings, log pond, rail connections. The mill's output, if operating at capacity, could generate sufficient revenue to recover that investment within a few years. The economic model drove rapid mill construction and drove the production pressure that directly affected maintenance decisions and worker safety conditions. The steam-powered era in the timber industry reached its production peak roughly between 1905 and 1915. Several factors converged to produce that peak and then to shift the technology base. The first factor was fuel cost and availability. Steam equipment ran on wood or coal. In a logging operation, wood fuel was initially available as a byproduct, mill waste, bark, logging slash. As operations expanded and moved to areas where that waste stream was less convenient, fuel costs became a larger operational consideration. The second factor was mobility. Steam equipment was heavy. Moving a steam donkey to a new yarding location required significant effort. The machine was skidded on its timber sled, which required its own rigging to move. A large donkey might require the better part of a day to relocate. This limited how rapidly the operation could advance through the timber. The gasoline and then distillate-fueled internal combustion engine began appearing in logging applications in the 1910s. Early gas-powered tractors had significant limitations. They lacked the pulling power of a steam donkey under sustained load. They overheated in heavy work, and their fuel systems were not fully reliable in the field, but they were lighter. They started faster. They did not require a sustained fire to build pressure before work could begin. For certain applications, particularly skidding on relatively flat ground, they offered advantages. The diesel engine, which arrived in practical mobile applications in the 1920s, was the more significant development. Diesel offered the torque characteristics that heavy work required, with fuel economy superior to gasoline and without the water management requirements of steam. A diesel-powered machine did not need a water supply. It did not require 45 minutes of fire building to develop working pressure. It could be shut down completely and restarted within minutes. The Caterpillar Tractor Company, formed in 1925 from the merger of Holt Manufacturing and C.L. Best Tractorcom, produced diesel crawler tractors that directly replaced the steam donkey in many logging applications through the 1930s. The crawler track concept, which Holt had developed for agricultural tractors on soft ground beginning in the 1900s, and which the Lombard log hauler had applied to logging transport, became the standard platform for heavy logging equipment. The transition was not overnight. Steam donkeys remained in operation in some Pacific Northwest timber operations into the 1940s. Where the timber was difficult enough, where the capital investment in existing steam equipment was sufficient, operators kept running what they had. But new capital went to diesel. New operations were built around diesel power. The large steam sawmill also transitioned, though the driver was electric power rather than diesel. Electric motors, connected to the expanding utility grids of the early 20th century, offered significant advantages over a central line shaft. Individual machines could be driven by their own motors, eliminating the belt drive system and its associated failure modes. Production could continue on other machines if one motor failed. Speed control was more flexible. The fire risk associated with the steam boiler was eliminated. By 1930, new sawmill construction in the Pacific Northwest was predominantly electrically driven. Steam-powered mills continued operating until economic obsolescence made replacement necessary. The specific machines are gone. The operational steam donkeys are museum pieces or scrap. The Lombard log haulers, fewer than a dozen, are known to survive in any condition. The large steam-powered head rigs of the Pacific Northwest mills were scrapped for steel during the Second World War, when metal drives collected industrial equipment across the country. What remains is the engineering inheritance. The crawler track system that the Lombard applied to a log hauler in 1901 is the foundation of modern heavy equipment. Caterpillar excavators, bulldozers, military tanks. The principle, continuous track distributing load over a large contact area, did not change. The materials changed. The power plant changed. The application of the principle did not. The industrial boiler, refined through the disaster record of the 19th and early 20th centuries, became the basis of modern power generation. The failures, the crown sheet collapses, the riveted seam failures, the unchecked pressure events, produced the regulatory framework and the engineering standards that govern pressure vessel design today. The American Society of Mechanical Engineers published the first boiler and pressure vessel code in 1914, directly in response to the documented failure record. Every pressure vessel manufactured in the United States today is produced under the descendant of that code. The code exists because of what happened when it didn't. The occupational safety framework of the modern workplace. OSHA standards, machine guarding requirements, lockout-tagout procedures, fall protection, was built partly on the documented injury record of industries like logging and sawmill operation. The statistics that state labor bureaus began collecting in the early 1900s, incomplete as they were, eventually built a body of data that supported the argument for regulatory intervention. The argument was not made on moral grounds alone. It was made on documented injury rates. The forests of the Pacific Northwest are different now than they were in 1900. The accessible old-growth Douglas fir and redwood that the steam-powered industry harvested is largely gone. What grew in 250 years could not be regenerated in the logging cycle. The industry that continues operates on second growth and managed timber, with equipment that the 1905 engineer would not recognize in its specific form, but would understand in its operational purpose. The sawdust from the 1905 mills is gone. The mill ponds are filled or drained or converted. The skid roads through the old-growth timber are grown over or eroded into gullies. In some areas, the compressed soil of old logging roads resists revegetation more than a century later. The railroad ties that the industry produced are in the ground under active rail lines across the country, replaced periodically as they rot or shatter under wheel load. The framing lumber in houses built in the early 1900s is still standing in buildings that haven't been demolished. Old-growth Douglas fir, cut to dimension and kiln-dried or air-dried, is dimensionally stable and rot-resistant in a way that second-growth lumber is not. There are builders today who specifically seek reclaimed old-growth timber from demolished early 20th century structures because its physical properties are superior to what the modern timber industry produces. The steam donkey did not retire gracefully. It was replaced by something more efficient, cheaper to operate, easier to move, and less demanding of fuel and water infrastructure. When a logging company bought its first diesel tractor, the steam donkey went into a corner of the equipment yard and then it was sold for scrap, or it was abandoned on the hillside where it had last operated and the timber grew back around it. There are a few of these still out there, on hillsides in Oregon and Washington. In the logged-over interior of British Columbia, the iron is rusting. The firebox bricks have long since collapsed. The cable drum has seized. But the basic form is still visible. The boiler shell, the drum housing, the timber sled. You can look at it and understand, from the engineering, what it was built to do. The mills are gone. The company towns are gone or converted. The men who operated these machines worked their careers and retired or did not retire. And their children moved to cities and did other work. The specific knowledge of how to read a boiler pressure situation at 3 in the morning on a cold shift, or how to tell from the feel of the carriage that the head rig was beginning to wander, that knowledge was not written down in any systematic way. It was transmitted person to person, shift to shift. When the machines went, the knowledge went with them. What was built out of the timber these machines processed is still standing. The cities, the railroads, the grain elevators, the warehouses, the early 20th century residential neighborhoods that contain houses built from old-growth Douglas fir and Sitka spruce and coastal redwood. The machines are gone, the material they produced remains. The forests that supplied them are largely replaced by younger growth, managed for commercial harvest on a rotation cycle measured in decades rather than centuries. The industry built the machines it needed. The machines produced what the economy required. When better machines became available, the old ones were replaced. The engineering problems that produced the steam donkey, the Lombard hauler, the steamhead rig, the line shaft mill, those problems were solved. And then they were solved again with better technology. And they will be solved again in forms we don't yet recognize. That is how industrial technology works. It solves the problem in front of it with the materials and knowledge available. It does the job it was built to do. And then it is replaced.